Okay, thanks for coming. Thanks for inviting me. So I'm going to talk today about my symbolic regression package, SymbolicRegression.jl. So this is a machine learning package written purely in Julia for doing model discovery with genetic algorithms. So I'll first thank the various contributors. So these are the people I work with in kind of the science applications. And then there's a long list of GitHub contributors. I'm sure some of you are here. I'm not good at faces, so if you are, feel free to chat after. So I'm going to talk about really kind of 4 packages. So the main package is SymbolicRegression.jl. This is a package for discovering expressions that fit data. There's also PySR, which is kind of a Python wrapper. And then the 2 kind of backend packages are dynamic expressions, and then this new package, dynamic quantities for unit evaluations. So I'm going to start with the motivation. So like, why do I want this? So I think, so my background is science. I want machine learning to give me a model that I can understand. Like I want it to give me a model in a language I can understand. This has many benefits, so I can get insights into existing models. I can understand the biases of my model. I can understand if it has some kind of weird learned shortcut. And I can place stronger priors over the space of models. So luckily, science already has a modeling language, which is very good, and that is math, right? So you know, in computer vision, like I think part of the reason we like to use convolutional neural networks and just really flexible models and train them on a lot of data is because we don't really have a language for, say, describing an image of a cat, right? But we do have a really good language for science, mathematics. It's very accurate at modeling the universe. So I think the problem here is that if we have kind of this knowledge embedded in a model, we don't really get insights out of that. So if you look at the history of science, a lot of the time there has been some empirical discovery of some law. So maybe Kepler's third law would go on to motivate Newton's law of gravitation. Planck's law is actually, that's another empirical equation that was discovered with some kind of theoretical motivations, but that would require quantum mechanics to partially explain that. Whereas if you have some neural network and it's just all kind of embedded in this parameter space, you don't really get insights out of it. So I think, so this is just some cheat sheet for Physics 101. You can see so many relations in physics are just simple expressions. So this is a really good prior, not only for building general models, but also for interpretability, because you can kind of, if you have a model in this language, you can see how it's related to your existing models. So symbolic regression, it's a machine learning task where the objective is to find analytic expressions that optimize some objective, some function, okay? So this was popularized by John Koza in the 1990s, kind of using genetic algorithms for this. And then Hod Lipson popularized this in science. So I really like this figure. This is from Jay Wadakar's paper. You can kind of have this, I forget the name of it. It's like some character diagram, but basically the outer ring is kind of the max amount. The inner ring is minimum. And there's 5 categories. So we have expressivity of model, high dimensional performance, interpretability, training speed, generalization. And we can compare symbolic regression, deep learning, and maybe decision trees. So like maybe XGBoost. And you can kind of evaluate the performance trade-offs and where you would actually want to use this. Because symbolic regression, it's not as expressive as, say, deep learning, but it's very interpretable, and you tend to get better generalization for physics problems. And then decision trees are kind of in the middle. So one other motivation for this, and by the way, feel free to ask questions throughout. I'm happy to take questions. So another motivation for this is something that we've kind of termed symbolic distillation. So if you have some, like the advantage of neural networks is they're very expressive. And so you can kind of use symbolic regression to understand neural networks and kind of distill them into my domain-specific language. So it's kind of an interpretability tool as well. Okay, so I'm going to talk through the methods now. Are there any questions on the motivation? Okay. Yeah, okay. Okay, so in many many symbolic regression methods, you represent expressions as trees. Generally, binary operators are all you need. So unary and binary operators. So for example, this tree, z plus 2 sine z, you can represent it as this binary tree, and then it has some representation in function space. So the way you explore the space of expression trees is kind of the best way to do this, which is a classical method, but it still works really well, is evolution. So you can kind of think of this tree as like a DNA sequence and just apply like mutations. You can apply crossovers. So if you have two expressions which are kind of good but in different ways, maybe you can like cross over parts of the expression tree. So the way the library SymbolicRegression.jl works is it uses this classic idea of evolution, and it basically just fine-tunes it and kind of generalizes it. And so the key idea is it's called age-regularized multi-population evolution. So if I have a population of expressions, okay, so maybe I have like 100 expressions, how I evolve this is I randomly pick some of them. So maybe I randomly sample 2 expressions from that population. Of those 2, I score them. So I evaluate their fitness, so maybe their accuracy in fitting my data. Then the one that wins that comparison, so we call it a tournament, you would apply some kind of perturbation to it to explore the space. So maybe you mutate it, you turn a division into a multiplication. You could do a crossover, so you could kind of mix 2 expressions. Maybe you do an algebraic simplification, or maybe you do a constant optimization. So you basically just, like, the idea is really simple. You just go through this loop, and you just try to make this loop as fast as possible. And all of these operations kind of optimal. Like you want to have good weightings on the different pathways. But the key, like, there's not really any crazy like deep learning or anything. It's evolution. You're basically simulating evolution on expressions. So there's a few things that SymbolicRegression.jl does. So one of them is parallelism. You can think of this as every population of expressions lives in either a thread or a process, and they evolve independently. And that lets you scale this up to thousands of cores over a cluster, because they can each evolve independently. And then once in a while, you have this migration step. So maybe this island sends over its best members to a different island, and they kind of exchange. So you can think of this as like, okay, maybe one island is specialized to maybe like polynomials, and maybe the other island is specialized to, I don't know, like trigonometry, and they kind of like exchange their best. So it really like tries to simulate evolution, and this helps it kind of explore the space, because it's not a differentiable space. Like it's really not nice to optimize in this space. So you need all these different tricks. So this is a video I spent way too long making, so I'm going to play it multiple times. But this is essentially how it looks. So you have this tree, and you're kind of evolving it to match that orange line. So you have like constant optimization, kind of adding a node at the top of the tree, another constant optimization. I'm going to play it again because I labored for this GIF. Okay. Yeah, so maybe you add a node, and then it's kind of exploring different pathways. Those are kind of like individuals. add another node. And this is how it explores the space. Like, it's not gradient descent, it's evolution. There are some strategies for doing gradient descent in this space, but it's you kind of run into numerical instabilities. Okay, so I'll talk about the library. So SymbolicRegression.jl is the core library. I designed it kind of, so when I started it, there was different kind of proprietary packages, and I was really kind of annoyed because people couldn't reproduce my results, because I was kind of like a user of symbolic regression, and I kind of became a developer out of necessity. So symbolic regression tries to satisfy the things I wanted. So I wanted it to be as high performance as possible. I wanted it to be as configurable as possible. And I wanted it to be easy to use. So symbolic regression really tries to do all of those things. So it gets high performance by, and I'll talk about this a bit more. It uses vectorized evaluation kernels. There's native support for distributed computation. It tries to be as configurable as possible. So you can pass it custom operators. They don't even need to be continuous. You can have custom constraints, like physics-based constraints, whatever. Custom types, so you can put in like fixed point floats, whatever. And custom objectives too. So easy to use. I'll show an API example soon. So part of the issue with exploring the space of symbolic expressions is that you're dealing with these dynamic expressions. Like, this is a symbolic, it's just a list of symbols, and I need to evaluate this really, really quickly. So if you just do eval in Julia, you don't get great performance, right? Because it has to compile and evaluate this. So symbolic regression was designed with this one struct called operator enum. It's basically a vector of functions. So I say, you're allowed to use these binary operators and these unary operators. You could also have like the first derivatives of those. But once you have this enum, then it kind of uses that to compile the evaluation kernels. So I'll give an example. So if I have this tree, right, this tree would be represented as this node type. So this is a mutable struct. It's all fixed. So it's kind of like a sum type, kind of. So you have, it's completely type stable, and you have a degree field, which basically says, is this a binary tree, or is this a binary node or a unary node or whatever? So for that green node, you can see it's a binary node, so degree is 2. It's not a constant, obviously, so it's false. There's no value stored, so that's just nothing. There's no feature, so maybe 0. The operator is an integer, so that's to make it really lightweight, because you're kind of copying these, you're generating a lot of expressions. So that needs to be lightweight. So that's just 3. Maybe it's the third operator in my enum. And then the L and R are just the children. Okay. Now, this is all fixed. So what happens is, if you have a tree with, if you have like a 1 degree node, basically it just doesn't assign anything to R. And so instead of like having, it could be the node or nothing. So the way it actually evaluates this is, it basically just traces through the tree recursively. So this is the example of a 0 degree node. So this is a leaf in the tree. It checks, is this leaf constant? If it is, it just generates a fill matrix with the same shape and the same type. So if it's like a sparse array, you want, or I guess like if it's a static array, you want also a static array. And then if it's not a constant node, so it's like a feature node, then you just index. The second flag here, that's just like a technicality. It's basically just a faster way to deal with NANDs rather than having to do a try catch. So you get really good performance when you start doing things like fusing functions. So this example is a evaluation kernel for a 1-degree node followed by a 2-degree node. And so what it's doing here is it's specialized to the operator and the child operator. And what that lets it do is put all of those operators into the same for loop. So it can just go really, really fast. And it's essentially like it compiles the cosine, maybe it's like a cosine and a plus, and it will compile those into the for loop rather than needing to get those dynamically. So when you have that, you can get down to, say, like 700 nanoseconds rather than 117 microseconds. So by having these like an enum over operators and then just fixed evaluation kernels, you can get much, much faster performance. Even when you do things like randomly changing the expression, you can still get really nice speeds. And speed is everything for genetic algorithms like this. Like you just want to go through that loop as fast as possible. There's some other nice things. So in this node type, you can kind of treat it like a collection, which is really convenient. So for example, if I want to get a list of all the degrees in the tree, I can just use map. If I want to check, is this tree like constant or does it have some variable? I can just do a all and just treat the tree like a collection. So it'll just do a depth first traversal. And that's just useful for doing like custom constraints or objectives where you need to symbolically manipulate it. Okay, so the way the library is structured is SymbolicRegression.jl is kind of the core equation discovery package. Dynamic expressions is that holds the evaluation kernels. Then these are the dependencies. So DynamicExpressions.jl depends on LoopVectorization for the fast kernels, and Zygote for compiling the first derivatives. There's also Optim.jl, and that's for doing constant optimization. So that kind of sits on top, and once in a while it does an Optim loop. There's also ClusterManagers.jl for cluster compute. So if you're doing like 1,000 cores on a Slurm cluster, you would plug in one of those. And then MLJ for the API. So those are the kind of the dependencies. There's downstream exports. So PySR, I mentioned earlier. So that's the Python version of SymbolicRegression.jl. That is connected with PyJulia. And that's kind of like a scikit-learn style library where the backend is Julia. And that has connections to PyTorch and SymPy. And then if you want to use like a computer algebra system, there's SymbolicUtils.jl. So there's a converter to that as well. So if you discover an expression, you can kind of export it to different libraries for downstream analysis. And yeah, there's a lot of other dependencies as well. Okay. So the way I'll just show a few other structures. These aren't that interesting. Basically, you have this population structure, and that just stores all the expressions. It's just a vector of pop members, and pop members have a expression and a loss, basically. There's a couple other things just for caching. But that's kind of the core data type. I'm gonna skip this one actually, but essentially what happens is, like I mentioned earlier, that each population lives on a core. So you feed in options and data set to this equation search function, and it just spawns populations on different threads or processes. And those kind of go through their loops, and once in a while they migrate. So they migrate between populations. So the migration actually really helps kind of explore the diversity of this expression space. That at the very end, you get the best expressions seen during the search. So this is what it actually looks like. So maybe I want to do a distributed search. So I do my add procs, I create this list of processes. And okay, so maybe I have So this is using the MLJ interface. And maybe I define some custom loss function. So this loss function looks at the squared difference in log space. I don't know, just some loss function. Then I create my model. So I'll talk about these steps. So this is an SR regressor. This is how you would typically use this if you're doing some kind of downstream search. You declare the operators it's allowed to use. So here it's plus, multiplication, minus, division. You could also have unary operators as well. The parallelism, this is like, do I want to use multi-threading or multi-processing? Both work, or you can do a serial search. Then the other thing, so I set my element-wise loss. So this is like the loss I wrote above. And then turbo equals true. This is like the loop vectorization. So these are the different hyperparameters for your search. You can customize these things as much as you want. These binary operators, they're any Julia function. Like they don't have to be, these are not special functions. Like they're just any Julia function you could write, you could have it as one of the operators. So you could even do, I don't know if anybody knows the fast inverse square root, that example. It's like this crazy, what? Yeah. So you can actually find that with symbolic regression because you can search for like the actual bits, which is cool. Yeah. The fast inverse square root, yeah, you can find it. Yeah. Yeah. I mean, it takes like a lot of cores, but you can find that. And you would basically declare some binary operators that do bit manipulations. Yeah. Okay, so I declare my model. Then, so this is MLJ stuff. So I say this is my model and my data. And then I do a fit. Oh yeah, so this is my actual data. So this is the Ames housing data set. It's basically trying to predict housing price from a list of variables. Create my machine, and then I'm gonna fit. So I've allocated some processes. Maybe these are on some cluster, whatever. I'm gonna do my fit. And this is what the output looks like. So, I mean, this is the first time, so it's gonna compile everything. It's gonna set up the workers, and then it's gonna do this. So it's gonna give you this output. So this is a table of the best expressions seen at each complexity. And you can see, so it's used the variable names that we gave it in a table. And you can see like these are the predictions for housing price as a function of the variables. You can see the loss column, the complexity. And so like the complexity 3 expression is like the living area. That seems like it should be correlated with housing price. And you can see like as we add more complexity, you get more accurate fits, but it's maybe less interpretable. So this is really quick. Like this is not a full search, but you can see it kind of gives you nice interpretable expressions this way. So I'll just skip through. Once we have that, we can do report. So you can do report of the machine, and it gives you lists of expressions. And maybe I want to convert it to like symbolic utils. So I can do node to symbolic and get like a symbolic expression. And then I can use this in a computer algebra system, simplify it, right? Like I can do simplify, whatever. Okay. So I'll just quickly mention the Python API if relevant. So I mean, like most Python libraries are kind of like C backend, Python frontend. So PySR is kind of like Julia backend, Python frontend, which I think is a really interesting space to explore to kind of get those users who may not use like pure Julia libraries, but you can kind of access a larger market essentially. So PySR actually has more users than the Julia version, even though all the algorithms are on the Julia side. I'll show some quick examples. So this was a really cool paper by this student at Madison, Wisconsin, and some people here at MIT. they use SymbolicRegression.jl to find an optimal expression on an FPGA that approximated their neural network. So here, you treat complexity of an operator as the number of clock cycles on the FPGA. So you're trying to find an expression that is essentially the fastest possible expression for that data. And so this is where Julia's multiple dispatch is really nice, because you can just stick in the native FPGA like fixed point number types and give the correct operators and whatever. So you can get this like, they have like a 5 nanosecond inference time on the FPGA, but it's like a 90% accuracy of the neural network. So this is like not really interpretability, but it's a nice example of how you can explore this space. So there's if you want to see the other papers, there's this list on this website. There's quite a few different like equation discovery papers that have used it. And I think I'll stop there, but so if you're interested in participating, I really welcome contributors. There's like a long wish list that I won't go through. There's like 20 different things I think would be really useful to have. Yeah, I'll stop there. Thanks. Take questions.
So are there any questions from the audience?
Yeah, great talk. And I got to email you. I keep on forgetting to. One question that came up though when looking at this is it looked like you had a fundamental instability in the way that you were doing the operators. Have you looked into using the beta version 1.10 opaque closures, or using function wrappers for handling the vector of operators? Because as of right now, as a vector of functions, you're going to have a boxing problem.
Yeah, so actually, the first thing I did was just have a tuple there, and so it would actually specialize to the operator, but I found it didn't really affect the performance.
Okay.
So I just did it as a vector, because then I can take advantage of pre-compilation.
Mm-hmm.
I mean, I might like try it again. Maybe there's other ways to kind of reduce performance, but essentially the kernel specialized to the functions. So even if you pre-compile with like a different enum, you get those cached kernels.
And what is the main overhead now, like at the current point?
Yeah, so I would say the main overhead is probably.
Also, do the features and operators, do they need to be ints, or could they be specialized to like int 8 and int 16 and such?
Yeah, so they could definitely be int 8. It's really, so it's still kind of the kernels, like the evaluation kernel. So that is still kind of the bottleneck, even though it's been like so heavily optimized. So some things I've been kind of experimenting with is I mentioned this like fused kernel. So you could think about just like having a general kernel that can fuse like any number of operators. I haven't gotten it working as fast as I want. So it seems like 2 operators is kind of the limit, but I think that would be interesting to try, because that is still kind of like the bottleneck. The algorithmic side, I think choosing the correct weightings of the different mutations, that's kind of the algorithmic limitation right now.
Yeah.
So there's some like MCTS approaches, and I think those would be really cool to try.
Yep, super cool stuff.
Thanks.
Any more questions?
First of all, thanks for the great presentation. I had a small question. So earlier in the presentation, you showed how different populations interact and can cross over, but because it's an embarrassingly parallel problem, in practice you choose to sort of implement this in independent tasks and processes. So
Implement what?
Implement the populations actually growing in their own independent processes, right?
Yeah, so they migrate between each other.
So yeah,
and there's the crossover. So the crossover is kind of like a mutation. Like it's like within a population, you could randomly kind of like breed 2 expressions.
I understand.
Yeah.
So how do you basically implement crossover between 2 populations, and does that not?
Oh, so you only get crossover between 2 expressions.
Okay.
The way populations mix is migration, and so there's no actual exchange of like expressions here. It's just you're cutting up part of a population and moving it to the other one, and vice versa.
Thanks.
just if you go back, I think one slide, or yeah, that one. So with your sort of randomly sampled set of expressions, now you say that you just replace the oldest. Now I've got a colleague who's been doing a lot with evolutionary approaches and expression building using actually stack-based languages, but he's spent quite a bit of time investigating different strategies with actually managing the population of available expressions. In his case, functions. I was wondering if that's something you've investigated much. For example, having a sort of semi-curated subspace of diverse expressions, for instance, instead of just having the newest ones.
Yeah, I think that would be really interesting to explore. But yeah, I haven't investigated it thus far. The replace oldest, so that is like I think it's maybe, I don't know, it's a bit newer in genetic algorithm sense. So it's like maybe 10, 20 years old. And it's called age regularization, because traditionally you would replace the worst expression. But here you replace the oldest. But I think in general, it would be really interesting to try managing the population like with different summary statistics and optimizing for different things rather than just age. I think that'd be cool.
I guess we need to clarify the rest offline. I have a couple of questions myself, but I will talk to you later on.
Thanks.
So thanks to speak again for the great talk.